All right. So in proofs, we've got two components that we have to master. The first bit's the nature of proof, and then the next bit's inequalities. I think because we've got limited time, I might actually go through inequalities because that is something we can get working on straight away. The nature of proof, it is very so like in university math, there are two components. There's one component that's called pure mathematics, and then there's another component that's called applied mathematics. Pure mathematics is this whole concept of the nature of proof. It is very annoying. There's a lot of interesting and new terminology, new symbols that you've got to get your head around. It is very theoretical in nature, and it's the proof of absolutely everything in mathematics. So unfortunately, it is very complicated, and it's not done very well. It's not written very well because it's very traditional, I guess, in a way, because of the writing. You can't make it any easier. The inequalities bit, however, I think we'll get started on that today. That will make sense to you, and I think you will enjoy it a lot more than its nature of proof. We've already finished induction, by the way, right? So induction, there's nothing else there to do, just a bit of practice. But that's kind of what I mean. Like, you've got to learn that n now means the set of natural numbers, z is a set of integers, q would be the set of rational numbers, r is the set of real numbers, and then an upside down capital A is for all, and there's a few more as well. So don't worry. But I'm saying there's a lot of annoying stuff. So what we'll do, we'll actually head to inequalities. Yep, we'll head to inequalities. And we'll get started on this for today. So, all right. All questions hinge on one or more of the following results. Either that A is greater than B, A is equal to B, or A is less than B. So the idea would be if A is greater than B, then you can actually say that A take away B is greater than 0. Right? If A is greater than 0 and B is greater than 0, then you can actually also say A plus B is greater than 0. If A is greater than 0 and B is greater than 0, you can also say the product of these two things are greater than 0. Perfect squares. You can say that A minus B all squared, if that's greater than or equal to 0, always, right? That's always. A minus B all squared is equal to 0 if and only if, so if you ever see an I, double F, if and only if A equals to B, then this would equal to 0. Wait, do we understand 5? So that one we're going to use a lot of. So A minus B all squared is greater than or equal to 0. We're going to use always. It's always greater than or equal to 0. But A minus B all squared is equal to 0 if and only if A is equal to B, of course. And then A plus B all squared is also greater than or equal to 0 always. But A plus B all squared is equal to 0 if and only if A is equal to negative B. Yep. Multiplication by positive constant. If I've got A is bigger than B and equal to B, so if A is bigger than or equal to B and C is bigger than 0, then I can actually say if I multiply both of these sides by C, the inequality will still hold true. So AC would be still bigger than or equal to BC. If I multiply by negative constant, so if A is bigger than or equal to B and C is less than 0, then you would say that AC is smaller than or equal to BC. Okay, be careful there. Again, if 5 is bigger than 3, if I multiply both sides by negative 2, actually becomes negative 10 is smaller than negative 6. So your inequality sign changes here. If A is greater than or equal to B, don't worry, you won't need all of these. Some of these just make sense, right? Most of these is just logic. So don't stress and think, oh, I got to learn all these rules. You don't have to. You only learn what I tell you. So far, I've only started the first thing here. If A is greater than or equal to B, and B is greater than or equal to C, and C is bigger than or equal to D, then you can say that A is bigger than or equal to D. Again, look at it. 10 bigger than 8, 8 bigger than 6, 6 bigger than 3. Then you can obviously say 10 is bigger than 6, 10 is bigger than 3. So A is bigger than B, bigger than C, bigger than D. Addition rules. Maybe a little bit less known. If A is smaller than B and C is smaller than D, then A plus C will actually always be smaller than B plus D. So A, two small numbers, always be smaller than the two larger numbers. If A is bigger than B and C is bigger than D, then again, your two larger numbers will be bigger than your two smaller numbers. Multiplication. If A is bigger than B, and that's bigger than 0, so they're positive, and C is bigger than D, bigger than 0, again, positive, then A and C would always be bigger than or equal to B and D, and A over D, so a big number over a small number, will actually be larger than a small number over a bigger number. You see how this works? Right? You know that's true, but you don't think like that, do you? But you got to start, I guess, with inequalities and proofs. It's time to start thinking like this. A small number, again, let's do it one more time. Sorry, a large number over a small number will be bigger than a small number over a large number. Right? Because you know over a large number means this number becomes smaller. And over a smaller number means this number is going to become larger. All right. Don't stress. Then you've got arithmetic mean, where that's just your basic average, A plus B over 2. And then you've got your geometric mean, square root of AB, or AB to the power of a half. We get this very famous arithmetic mean, geometric mean inequality, which we're going to prove shortly, where you get A plus B on 2 is always bigger than or equal to the geometric mean, square root of AB. All right, very famous inequality. Don't worry, everything's got to be proven. Nothing here can be memorized except this particular one right here. So let's do this. X minus y all squared is greater than or equal to 0, right? From that, we expand and we can conclude this. X squared minus 2xy plus y squared is greater than or equal to 0. From that, if I add 2xy to the right-hand side, I end up with this result. Now you can see if I said this bit, let x squared equal to, let x squared equal to a, and let y squared equal to b, what would you end up with? You'll end up with a plus b is greater than or equal to, well, that's x, y, so square root 2 root a, b. And then can you see if I divide by 2, I end up with this result. So you're going to get a lot of inequalities from this, a lot. So this is the one to memorize, and I guess this step, knowing that you're allowed to substitute. Okay, any questions at this stage? Beautiful. Hubert, the person who teaches from Normanus here, he says add 4xy. I don't say that. I say just move your 2xy to the right hand side. I think it makes a bit more sense than adding 4xy to both sides. But anyways, again, each teacher to their own. Enumerating multiplied terms, prove that yeah. All right. I don't know if we're ready for that. Maybe for this. Is this? Yeah, maybe that. Maybe we'll start with this one. Okay. Suppose P, Q, and R are real and distinct. Prove that P squared plus Q squared is greater than 2PQ. Okay, because they're distinct, which means they're different, right? So we know now P minus Q is always going to be greater than 0. So therefore, and not equal to 0. So therefore, you're going to get P minus Q squared greater than 0. And then, of course, you expand. And you bring it to the right-hand side. So I think that first step should always be the easiest mark you're going to get in your exam. Right? That's simple. Done. B. B says, hence prove that P squared plus Q squared plus R squared is greater than PQ plus QR plus RP. Now, what can happen? Firstly, you can see that you don't have an R, right? But what can happen is if I have this particular relationship between P's and Q's, I can actually have the same relationship, just like you saw with those dummy variables, questions that I wrote before. You can have the same relationship with P and R, right? They're just letters. And same thing with Q and R. Okay? So when you're going to have now 3 of these, so P squared plus Q squared plus R squared, you understand you first start off with that. Then what you do is you rewrite the similar results for your other letter. Then from that, because you can see they're all added, you're going to add everything. So you're going to go, okay, P squared plus Q squared plus P squared plus R squared plus Q squared plus R squared must be bigger than 2PQ plus 2PR plus 2QR. Right? Your left-hand side must be bigger than your right-hand side. On the left-hand side, you will get P squared, 2P squared, 2Q squares, and 2R squares. And some of you might see, I pretty much have the result. I've got an extra 2 everywhere. You just cross them out, and you're done. P squared plus Q squared plus R squared is greater than PQ plus PR plus QR. And again, this needs to be, I'm hesitant in saying memorized because A should be the one that needs to be memorized. Everything else is just results. But yeah, a lot, like 99.9% of students do memorize these particular results as well, just so they can remember when I've got 3 terms like this, I am going to add them. If I've got a cubic, I'm going to do this. If I've got a quartic, I'll do this, or whatever. So you'll eventually memorize through practice because they get pretty repetitive, the inequalities. But it's important to understand your very first step more than anything. Okay, we'll come back to C. I think I'm pretty happy with that. If you can get that out, I would just want to finish off these 2 so we can understand how these work. So we're going to use this particular result, right? We're going to use the result that A plus B, we're going to use it, but of course if the question was to do this, you have to know to prove it yourself. How would you recognize to prove it? It's because it says a plus b instead of a squared plus b squared. If it was a squared plus b squared, you would have used that one. Because a plus b, actually I'll show you how to prove it in a different way. So best proof one, I mean, what I did is I just did it with x minus y and then let it equal to. Another clever way to prove this result would be root a minus root b squared. That must be greater than or equal to 0. Right? And then when I expand this, look what you get. A minus 2 root ab plus b must be greater than or equal to 0. And then you end up with the same result of your a arithmetic mean and geometric mean. Your a and g. So you've got this. That's fantastic. But then you wanted this. So we've got this so far. A plus b on 2 is greater than or equal to root ab. Now think of the logic that I just showed you down there. What are you guys going to do? Tell me what would be my next few lines, or what would be my next line even? So I don't have a plus c or b plus c. So what would be my next lines? Wouldn't it be a plus c on 2 greater than or equal to root ac? And what about b plus c on 2? Root bc. Yeah? Now, how do you think I'm going to get this result out? Can someone tell me? What would you do to get the result out? Azra, what would you do? You've got these three things. You need to get this result out. What would you do in the next line? Anouk?
Would you add them all together, like the last one?
You think so, though? So look, a plus b on 2 plus a plus c on 2. Do you think that looks right?
No.
So what are you going to do?
Or would you times the 2 over?
Yeah, that makes more sense, doesn't it? You're going to times it all together. That's completely allowed, right? Greater than or equal to root AB, AC, BC. So A squared, B squared, C squared. And then I think you guys can see that cancels out. 2 times 2 times 2 is 8. And you're done. So it's really important to see that you can get your first result out, because you're not meant to think of this as a whole proof of getting the whole thing out. Right? It's only meant to be the first bit, and then you extrapolate or enumerate the rest. So continue. This is multiplied because it's got a multiplication between them. If I show you another one, I'll come back if you're copying here. So if I got the result a squared plus b squared is greater than or equal to 2ab, because of you expanded, I'm assuming you guys get this, then if I end up with this result, that's the one that you're probably going to add, because that would make sense. All right, I'll pause there. Any questions? Have I ever lost anyone? Not yet. What do you think? Confusing, of course, but are you keeping up with it? Is it making sense?
Yeah, I think I'm if I go over it, I'll be able to understand it better.
The most important bit is just that squared bit. So the fact that you can have two things squared, and that's going to be greater than or equal to 0. And then once you've got these results, you can either end up with, that's just another way of doing it. I'll write here, another way. Otherwise, you could have done it the traditional way, which would have been just starting with x's and y's, and then changing your x squared for a and y squared for b. All right, here it is. Suppose p, q, and r are real and distinct. Prove that p squared plus q squared is greater than 2pq. There you go, right? I did p minus q squared. The only reason why it's not equal to is because it says it's distinct. So we already know they're different. So they don't equal to. Hence prove that p squared plus q squared plus r squared. There it is. Now, this last bit. Given that p plus q plus r is equal to 1, prove this right-hand side is less than a third. Okay. All right. Given p plus q plus r is equal to 1. So many different ways of doing this. Oof. How to do this one? How to do this one, son? Given that p plus q plus r is equal to 1. And this is the bit with proof that's a bit annoying. There are no exact methods of doing things. So I'm just trying to see if it works out like this. Let's see it. No, it's right there. Hence prove this. Given that p plus q plus r is equal to 1, prove that p2 is less than 4. I think I had it the first time. So p plus q squared plus r squared is greater than pq plus qr plus rp. Right? We know that p squared plus q squared plus r squared can be written from polynomials as a perfect square like that minus 2 times some of its 2 at a time, which is this, pq plus qr plus rp. Do you guys remember that rule? Alpha squared, just write it. This one here is equal to alpha plus beta plus gamma all squared minus 2 times sum of roots 2 at a time. So p plus q plus r squared is 1 minus, yeah, because they gave you that, p plus q plus r is 1 minus 2 times this, So plus this over becomes 3 times. I'm just going to write 2 times capital A, just a bit easier to write. Greater than A. 1 is greater than 3A. Therefore 3A, what do they want? 3A is less than 1, which means A is less than a third. Therefore PQ plus QR plus RP is less than a third. Okay, so that one there, they related polynomials. I guess what gave it out to me when I first started it as well was the fact that they said P plus Q plus R, and when you think of a perfect square, or P plus Q plus R and this particular identity, usually this comes into play. I love that, brute force your way through this, because that's honestly the way you've got to do some of them. I just want to do one more particular result. I don't know if he's got it in here. Yeah, it doesn't really have it in here. It is kind of there in this one, but I'll just... Oh, he does, in A. Okay, perfect. So, imagine we have to show a question like this. Let's see what you guys get to, right? Show that if A is greater than 0, we want to show A plus 1 on A is greater than or equal to 2. All right, I can tell you, you will start with this. I mean, you don't have to, but it is the right one to start with for now until you get used to it all. So x minus y squared is greater than or equal to 0. Then from that, you get x squared minus 2xy plus y squared is greater than or equal to 0. From that, I think you're understanding, we usually write this. Okay, now I want this result. Can anyone see how to go from this to this result? It's not that hard, but you just got to say to do something. So here, let. Any ideas? Let x squared equal to a, and let y squared equal to 1 on a. Therefore, you would end up with a plus 1 on a is greater or equal to 2x, which is root a, times 1 on root a. These cancels out, and there you go. So it's important for you to understand that every result initially that you're going to have is actually going to come from this guy, regardless of how it looks, because you can let it be something else. It's just your other results, like these ones here that are multiplied and whatever, no. They have to come through, I guess, algebra. Alright, I'm going to save this, send this as well to you guys. And solutions. And then, I guess, next week. So this is what I'm thinking of doing.